Okay. Hello, hello. Is this on? Yeah. Okay. Okay, hello everyone. I hope everyone is well caffeinated for the tutorial. So I prepared a number of tutorials. I hope you got Docker to work. If not, then let me know. I heard there was several problems with Macs. We may have a solution for that that just developed. So if you run into trouble with that, let us know or let me know, and I'll try it. Yeah, we'll try in concert to make it work. There are three types of tutorials. So the LL stands for leading log. You can build a next to leading log resummation, despite of what the name says. But you start with leading log, obviously. There's the PS tutorial, which lets you build a Parton shower. Now, we haven't covered the Parton shower in the lecture yet. However, if you like, you can start with that. So it's kind of a la carte, right? Depending on what you would like to do, pick your favorite, right? Or you can build a matrix element generator. So if you want to go in depth with what I covered in the lecture today, you can build a matrix element generator for 3-jet, 4-jet, 5-jet, however far you get process, according to the principles that I explained in the lecture. Each of those subdirectories has their instructions. So there's a worksheet in here, which explains in very much detail what you need to do. If you have trouble with any of this, let me know, okay? So it is designed such that if you take the typewriter type fonts, type lines here, you dump them into a file and you pay careful attention to the spaces. So you can do drag and drop if you like, or you can type it up, whatever you like. Then you will get a working code. This is also the reason why there's indentation here, because it's Python. So pay attention to the spaces. Each and every piece of what goes into this generator is described in the text which is in between those Python lines. Okay? So I suggest that you probably just follow this, and whenever there are questions, we can discuss it either in private, or we can go to the Blackboard, or we can discuss it with everyone. Depending on how things develop, it's a la carte. So we do this whatever way you prefer. There are three types. This is the hard process. In the end, you will be able to run a generator for 2 jets, and you can extend it to 3 jets, or you can do other fun stuff with it, depending on what you feel like you want to try. The Parton shower tutorial will make a little more sense after the lecture tomorrow, I think, but you can still try it out. It's totally up to you, because it has all the instructions in here, and if you're already kind of familiar with the terminology and what a Parton shower does, there's no problem with just going ahead with this and asking questions, okay? And then if you are adventurous and you say, I always wanted to know something about resummation, you can try the resummation tutorial. Okay. For all of those, it's more or less the same. You use, it's convenient to use this alias to define a Docker run command, but you can run it any way you like. It's totally up to you. Everything that you need should be in the container. Have fun. And ask questions. Yeah, go ahead.
Are these tutorials for the whole week, or just today, and there will be more for the other days?
So we had 3 blocks, and this is designed such that it will likely be more than what you can do in those 3 blocks, but there is stuff that you can take home and think about, right? So for example, the Parton shower tutorial. So the matrix element generator tutorial is kind of new, so you're kind of the guinea pigs. I'm still testing this out. The Parton shower tutorial is kind of more developed. In the beginning, you construct a generator for E+ E- to jets, and you will be able to compare the output to a state-of-the-art Parton shower, and you will find that it gives exactly the same answer. And then you can play. So you can do on-the-fly uncertainty estimates, which is technical, but somehow exciting. You can do matrix element corrections. You can do next to leading order matching either in the PowHack method or in the MC at NLO method. Just to demystify this, that is not a secret. You can do it in a couple of lines. If you have already heard about those methods, you would like to understand them in detail, go ahead. There's more than enough things to play with. And let me know if you like have questions, right? Yeah, but to answer the question like from a different perspective, so these 3 tutorials are for the 3 blocks of tutorials that we have on the 3 afternoons. Typically, the shower tutorial will take more than 1 afternoon. No, so you have to download them. You just follow those instructions here, basically. Oh, sorry. Yeah, sorry. I should have said that. So to download that stuff, you go here, right? You say, okay, git clone with HTTPS, and you get this from GitLab. Yeah. If you have trouble with that, let me know.
Whichever.
I'm just trying to make this.
Yeah.
So it didn't work if I just put in the timer. So I just put in my bash RC, but it still says that.
Okay. Didn't like it.
Okay, there's still the permission thing. But I already managed to pull in everything.
Okay, that's good.
But it doesn't exist even though I just define it. But okay, if I just run this.
So what happens if you do, let's say, Docker image ls, for example? Oh, sorry, I should turn the Perfect. Okay, let me just, for everyone, briefly just make a comment again. Sorry to interrupt you. I just wanted to say, so this tutorial is not like your typical, like, let's say, Metgraph tutorial, Hoeche tutorial, Sherpa tutorial, where you learn how to use a generator. This is not my goal. Because if you're going to go into this business of using generators more seriously, more often than not, you will encounter a situation where the generator does not do what you want. So the goal of this tutorial is to understand the inner workings of the generator, because once you know that, you can hack Metgraph to do what you want, okay? And therefore, we describe every single line of Python code that is in the generator and explain what it's doing. And if you have questions about that, let's discuss them, okay? A lot of the stuff is there as a teaser for you to think about. And the goal is really that you come with questions, right? I'm not interested in you running this code. I'm interested in you asking questions, what is in the code and why. So please ask questions. Okay, so let's discuss a function that in the code is called VT. It's kind of the first function that you will encounter, and it's kind of important, and I haven't explained it in the lecture. Okay, because I want you to ask questions. Okay, so these guys here are while spinners. So some of you may be familiar with them, some of you may not be. It doesn't really matter. They're just a way to write eigenspinners for the Dirac equation. And they are very convenient. So the P plus and P minus here are the light cone forward and backward momentum, or say the forward and backward light cone momenta. If I put my coordinate system such that, yeah, the three component is on the z-axis. Okay, and then I can write, I can write my transverse components as kind of a complex number where I put the x component as the real and the y component as the imaginary piece, and then I can encode the entire eigenspinner in these two numbers basically. And in the wire representation, I then have this chi plus in the lower two components of a four spinner, or the chi minus in the upper two components of the four spinner if I have massless particles. Okay, from that I can build massive particles, but we are not going to do this in this tutorial. The reason why this is interesting is because I have, because the Dirac or the gamma matrices take a very convenient form in this case. And the reason why it appears in the tutorial is because it allows us to define very conveniently polarization vectors that you may or may not have seen in the lecture on amplitudes. So if you use the helicity formula, was the helicity formalism explained in the amplitudes lecture? Yes? Okay, great. So you will probably, well, have you seen this equation? Let me ask like that. No. Okay. Did something like, okay, let me write it there. Oh, sorry, that's not a blackboard. So, yeah. Thanks.
I'll give you the screen.
So as we discussed earlier, this lecture is called From Amplitudes to Experiments, right? So we are turning the more abstract concepts of what may have been presented in the Amplitudes lecture into something that you can run as a code like Metgraph. Have you seen a relation like like this. In the lecture. Yes. Okay. Some say yes, some say no. Kind of.
Looks kind of similar to a bunch of other things we did see.
Okay, very good. Okay, let me get down to the physics of this. Okay, so this is a canonical way to construct the polarization vectors in the helicity formalism. Why is this a canonical way? Because what you see here is essentially a current coupling. So this is exactly the structure that you get when you have a fermion pair that radiates a photon, or a gluon for that matter. Then you have a coupling here which goes with gamma mu, and then you have spinors here, which in the helicity formalism are written like this, and typically they are abbreviated only with the indices. So you would find things like 1, 2 here or whatever, right, depending on how you label your particles. I just called them K and Q. So if K is the momentum of the gluon for which I want to construct a transverse polarization vector, then I would actually put that momentum into one of the spinors, and I would use another auxiliary vector Q to construct the other spinor. And then by means of this coupling here, I can construct a transverse polarization vector associated with this intermediate particle, kind of as the off-shell current for an on-shell particle. It's kind of a funny, funny misnomer, but anyway, this is kind of what we're doing. Why am I doing this? Well, I know that my gluon polarizations for external particles, for the external gluons, have to be transverse. This thing is guaranteed to be transverse. Why is it transverse? Guesses? I said that this vertex here conserves current, right? So the Ward identities are valid at this vertex, right? Which means that the current has to be transverse. That the polarization vector has to be transverse. So I have to satisfy, for any physical polarization, I have to satisfy current conservation. Okay. And this vertex will satisfy current conservation automatically because it's a physical Feynman rule that I actually get in like QED, QCD, whatever. So I conveniently use this to define a polarization vector. I could also construct my polarization vectors any other way. It doesn't matter. You can come up with your own basis, but this, and this is why I have this in the tutorial, is what you would do in the helicity formalism. So that's the link of the amplitudes from the amplitudes lecture to what we're doing here. What you would do in an amplitudes formalism is you would say, hey, I want to calculate matrix elements with many different gluons, but maybe I'm lazy and I don't want to do all the graphs. You can conveniently say, well, when I construct the polarization vector for this gluon here, because this is an external state, I take as a reference auxiliary vector here the momentum of another gluon. And that will guarantee that whenever these gluons meet at a vertex, that result is actually 0, because I will have to dot this momentum here to, at some point into this polarization vector. And by the properties of this current here, that will give 0. This is essentially the fact that Q slash times Q will give 0, equation of motion. Right. So that thing is encoded in the function Vt in the tutorial. How is it encoded? You take those Weyl spinors here, and you multiply them by gamma mu. Now, in the Weyl representation, these gammas turn into sigma matrices, which are located on the diagonal. So all I have to do is I have to take the Pauli matrices and I have to sandwich them between two of those states. And that's exactly what this function Vt does. The U1 and U2 members of the class that go into this little function are the upper and lower components of this while spinner. Okay, and you can convince yourself that what is encoded in this function is kind of not the Dirac version, but the while version of this, where you have a chi minus sigma mu chi minus of a different momentum, basically. Does that make sense, roughly? Okay. If you have more questions, let me know. Okay, so there was just another question again on that function and what it actually means. The function says something like, what does it actually say? Is it j of something dot whatever? There is something like a current or an epsilon that I return. Let me call it j. It's a current. Okay, that depends on some self.r3 or something like this, right? And that is calculated in a particular way. Okay. What does it actually do? So let's think about what I said about this, this decomposition of the momentum up there. I said that I can make P3 the Z component or anything else. And I basically leave it up to you, right? So you have the Pauli matrices. You have sigma 1, 0, 1, 1, 0. If I make a mistake with the signs, let me know. I never get this right. 0 minus I 0, sigma 3, 1 minus 1, 0, 0. Okay, so what this guy is, it's the sigma 3, okay? So it's for the mu equals 3 here, potentially, multiplied by those two spinors, okay? So when I multiply this by those two spinors from the left and the right, what will I get? I will get the first spinor. Let me call this chi q, and from this chi q, I will get the first component that I will have to multiply by the first component of chi k, which will be this element here, minus chi q second component times chi k second component. And that is essentially what appears here, okay? Now you can do the same exercise for those two components, and it will give you the thing where I have self.r2 and self.r1. However, I leave the choice of which coordinate axis that is completely up to you. You can say, I don't want this decomposition such that P3 is PZ. I want it such that P3 is PX. Okay. When you have P3 equals PX, you would set self.r3 to 2, then, to 1, then it would be the first coordinate in your usual way of writing things. And that is useful because when you have the full calculation assembled, you can rotate your Pauli matrices and check that you get the exact same matrix element out. It's not a gauge test, but it's a kind of Lorentz invariance check of the entire calculation that everybody in the matrix element community uses to validate their calculations. Does that make sense? Questions on that? Okay, if you have questions, let me know.